towards series fault, because almost all shunt faults with respect to LL, LG, and what is the effect with fault impedance, without fault impedance, all this parameter has been determined. Finally, we are going to find fault current in all the cases, and we got an idea that how to find the fault current, because in single question they are going to ask you to determine in terms of LLG fault, LG fault, LL fault. Just a small variations of the formula will going to give you the answer. But before that, as we said, we need to know the particular sequence diagram for the given conditions. So considering that, we are moving ahead with another type of fault system, that is series types of fault. So already we discussed series fault type. Also, we are having a three different types. So this is first one is one conductor open fault. Second one is two conductor open fault. And the third one is three conductors. 1, 2, and 3. Means based on the phases, we are dividing the system into three categories. First is one conductor open. Second is two conductors open. That the third one is three conductors open. What is that? So we know that there are phases: A phase, B phase, C phase. So this is A, B, and C. So here, whenever we consider a windings, so we are all familiar with this term of representation, right? We used to specify starting end, finishing end. So we write R, R dash. Similarly, if you have another winding, let us assume it is B. So we're going to represent as B, B dash. Here, A, A dash. So starting end, finishing end. C, C dash. So this is the representation of normal system, starting end and finishing end with respect to each phases. So we say that as a conductor 1, conductor 2, conductor 3. So if fault exists, so let us assume F is existing between one of the conductor. If this is exist, you are going to divide the system before fault, after fault. Before fault you are writing it as A, after fault it is writing as A dash. Means you are splitting this transmission line into two parts. As I said, if I have a 1 volt as a current flowing through this, so 1 amp, let us do 1 amps. So what you will do, you will divide this equally and you will write it as 0.5 before fault, 0.5 after fault. So simply we specify that substances are A dash, B dash, C dash. Okay, because your supply, whenever we give it, maybe a single phase supply, two phase system, three phase system, that may be a balanced condition. But finally, we are going to check about is the system getting a current. Where is the problem? Where is the fault existence? And at the same time, when you are considering with any machines, because unbalanced current flows in a rotating machines will going to cause a major issue called harmonics. So that's what the calculating the current is very, very important. Particularly rotating machine will going to cause harmonics. So that what happens? It will heat up the machine within a shorter time. So heat losses, finally it will going to cause short circuit fault. So heat, if it is increases, what happens? We say that immediately stop the operation of a machine, or else you isolate the machine from the healthy devices. So here we are going to solve this by using any of symmetrical component method, and we are going to analyze the equations. So three conductors, two conductors, and one conductors. So fault should be identified which side it is acting. Is it on the initial starting stage or the ending stage? So normally you are going to use the same common formula for symmetrical components. So with respect to current, you can write it as IA1, IA2, IA0, where it specifies the positive sequence, IA1 negative sequence, IA2, and last one is zero sequence, IA0. Individually, we are going to write the diagram for IA1, IA2, IA0 with respect to the fault condition. So fault condition, because we are dividing the system in terms of A dash, B dash, and C dash. And whenever we say the current is existing, definitely the voltage should also act, right? You need to find out two terminal quantity, one with respect to current and another with respect to voltage. So current in here we are written IA1, IA2, IA0. So here voltage should be calculated based on the fault condition. So you are going to consider as a common current, means variable current with different status. IA1 separate current, IA2 separate current, IA0 separate. But we are assuming every place voltage existence with respect to the phases. One will consider one phase. So VA A dash, VB B dash, VC C dash means terminal voltage across each of the system. Positive sequence network, negative sequence network, and zero sequence network will be considered. So if I write the simple diagram, so it will look like this. So you are going to have one of the system. Let us assume this is a positive sequence network. Okay, so I'll just write it as a positive sequence network here and current flowing through this. So this is the diagram. You're assuming fault is existing between these two. So what happens? You'll split up this starting and ending phases, right? So I'll write F and another one break. I'll write it as another point as F dash. So then the current will move like this. So IA1, IA1, IA1. So in between that, your voltage which is existing with respect to positive sequence, you can write as A dash into 1. Means suffix you are going to specify as 1. So this is for positive sequence. Similarly, negative sequence also same thing you are going to write IA2, F dash and A dash into 2. Similarly for zero sequence. Means suitably we need to interconnect depending upon fault. Is it of a one conductor, two conductor, three conductor? So this diagram we have written for individual specification. But if you have a combination of all the three, then we have to write the sequence diagrams. Fine. So this is the basic information about your series type of a fault system. So normally, as I say, there are various faults will occur. Shunt fault will occur, series fault will occur, and in that unsymmetrical faults, normally we call that as a open conductor faults. So it can be like one conductor or two conductor of a transmission line can be get opened. So this B get cancelled or B C get open or only A get open because majorly opening in the sense opening of conductor means what? Mechanical damages. So joint can be broken up or maybe some malfunctioning can be happen with respect to the fuses or for devising protecting the devices we can go for this system. So we need to analyze the fault which are existing in a series with the transmission lines. So you're going to have a transmission line. As I said, take an example, this is a transmission line. You're going to determine where is the fault existing in the series system, and that's what the name has been given, series type of fault. So here, when based on the open conductor as well as based on the series connection with respect to the transmission line, we segregated as 1, 2, 3 conductor open system. Okay, so again here also we guys are moving with the three different calculation. One is for one conductor, then two conductor, then three conductor. So take down the heading as one conductor open fault. One conductor open fault. I'll just show you the diagram. Please note down that. Yes. Take down the diagram of one conductor. Copy down. One conductor open fault. Means you are assuming, you can assume any phase. Not restricted that A phase only. You can take B or C or A. So initially first one is A. I'm considering that as a one conductor open fault. So IA, as I said, breaking with starting and ending, A dash, and fault between F dash. So whenever we see these diagrams, again, same procedure follow. Terminal voltages, terminal current, then fault current, and then what is VTH. All these regular parameters we are going to calculate. Just a minute, we'll take up the diagram and we'll solve the system. Okay. So first, when this is open, what you say? What is the current flowing through this series connection? It is broken, right? So I can write the initial condition of current IA is equals to 0. Next, with respect to this, what happens to the voltage? Voltage also get affected. So you are going to get VB dash is equals to 0, and the another one V C C dash is equals to 0. So first terminal condition has been calculated. So now we are going with symmetrical component relationship. So we'll find out for voltages. First one, positive sequence, you take it, that is VAA dash. So what is the standard formula we are having? 1 by 3. Normally we used to write VA plus A into VB plus A square into VC. But here that A, B, C has been changed with the term called B dash, C dash and A dash. So we'll write that as VA dash with the A operator, because this is symmetrical component, that is 1 by 3 we are using. So A will be the operator. We are going to get V dash plus A square into C dash. So now we guys are going to do the substitution. What is that VB dash? VB dash 0, VCC dash is also 0. So what is left out? We are going to get an answer called 1 by 3 into VAA dash. So first phase is over, positive sequence. Next I need to go for a second one, that is negative sequence, that is VAA dash. I think I missed out the representation. Positive sequence will be represented by 1, negative sequence is represented by 2. So I'll just make the small changes here only. So your same say answer will be almost same, 1 by 3 VAA dash, but in the place of A it become A square and the A square become A. So but the thing is VBB dash is 0, VCC dash is 0. Finally I'm going to get the same answer, that is 1 by 3 into VAA dash. Okay, second case is also done, and I've left out with last case, that is VAA dash. 0 sequence we are going to represent as 0 itself. So here also same thing, you're going to have 1 by 3 into VAA dash plus VBB dash plus VCC dash. So these two are 0. The left out answer is 1 by 3 into VA into A dash. So from this you guys are understood that voltage is constant in all the sequence of a network. Positive sequence, negative sequence and 0 sequence, your voltage is same. So that you can say voltage is constant. Okay, so we come to know about one of the parameter, that is voltage. So voltage is constant. But next, what we want to calculate? We want to calculate about current. So it is written IA is equals to 0. But what is this IA? IA is consisting of all the sequence, right? IA 0 plus IA 1 plus IA 2 is equals to 0. This whole term is represented as 0. Okay, so now considering this, you come to know about the system. We have a variable current and a constant voltage. Means symmetrical components are almost similar to your double line to ground system. Means your equations, current, you're equating with IA1 plus IA2 plus IA0 is 0, and voltage V is equals to 1 by 3 into VA into A dash. So when you compare these two, we can say it as a LLG fault combination. So considering that, we guys are going to write the network. But here what is that? Voltage is constant, current is variable. In which system we have this parallel series network? Voltage is constant and current is variable. So branch currents will be available in parallel network. So considering these two parameters, we have to write the sequence diagram. So in this, we are just writing the sequence diagram. We are not going for calculation of fault current and all again and again. Just we are concentrating about the network, how it can be written for one conductor open system. So we'll get back to the diagram here. So almost all the conditions are common. So let it be. So based on the terminal voltage and the terminal current, we can write the sequence diagram. So you can see positive sequence. Is it visible? Okay. So positive sequence, negative sequence, and zero sequence. As I written, PSN, voltage existing between the terminal FF dash, and current you can see IA1, IA2, IA3, and you are connected back all the F dash to one terminal, means two port. All F's are connected at the top end and all F dash are connected at the bottom end. So this is the sequential network for one open conductor system. Okay. Hope you can understood this. If you have any doubt, you can ask me. The same concept we are using for second two conductor open system and three conductor open system. Okay, guys, just copy down. Simple equations you copy down here. Diagram all of you taken right? Then write down the terminal conditions. Terminal conditions. And next to V8 A dash for negative sequence, then zero sequence. And finally, you write down the sequential diagram. Finished? Okay, take on the next heading, two conductor open fault. So first you copy down this diagram. So two conductor, they're chosen B and C. You can take A on B also, no problem. So B and C, they opened. Okay. So let's find the relationship with respect to voltage and as well as with respect to current. Okay, so we want the double conductor open system. Okay, so based on that, we'll write the conditions. So from the diagram, it is very clear the current through conductor 2, conductor 3, that is 0, means IB is 0. Similarly, IC is also 0. Then due to this, what happens? Current flow through the first conductor, but voltage will become 0. That is, you can write it as V A dash is equals to 0. So in this case, we have current parameters because most of IB and IC are 0. I'll go with the symmetrical component relationship in terms of current itself. So first one, I'll take it as IA0, then IA1, then IA2. So just write the standard formulas here and start substituting. So 1 by 3 into IA plus IB plus IC. So from the picture, it is very clear IB and IC is 0. So these two are 0. Then I left out with 1 by 3 into IA. Sorry. I'll just write out with the second case now. 1 by 3 into IA. Similarly, for the second case, IA plus A into IB plus A square into IC. But your IB, IC values are 0. Anything multiplied by 0 is become 0 itself. So the left out answer is 1 by 3 into IA. Means throughout all the three sequences, our answer is common. That is 1 by 3 into IA. So from this, hope you got an idea that current is constant. So current is constant for IA0 is equal to IA1 is equal to IA2. Current is existing common to all the system. Then we need to find out for voltage terminal values. So what they are given, VA A dash is equals to 0. So this is consisting of all the sequences. So VA A dash can be written as VA A dash 0 plus positive sequence VA A dash 1 plus VA A dash 0 is 2 is equals to 0. So it says that current is constant, voltage is variable. So in which condition we are going to get the sequence? Series network. So considering that combination, we have to write the sequence diagram. Series means what? It will be connected back to back. Means one winding to the another winding will be connected in a series connection. So we'll go back to the connection here. Series connection. Can observe here we have a positive sequence, negative sequence, zero sequence, and anyhow IA1, IA2, IA0. So you can observe here same voltages are existing, that is potential difference at each point VA-1, VAA-2, VAA-0. So connections you can see here. Positive sequence is connected to negative sequence is connected to zero sequence is connected back to positive sequence. Means complete to series connection you have done it. Means the current flowing through this complete system is common, path is common. Only one loop I am getting it. That's what it is connected from one end to another end, starting end to finishing end, finishing end to starting end. This connection has been done. So this is for two conductor open system. So please copy down this diagram for a two conductor open system. Two conductor open system. Finished?
Yes, ma'am.
Okay. So we have left out with one more case, that is three-phase fault, means three conductor. I think in that notes it is say it is completed, but of course we have to discuss about three conductor also, because when you say one conductor, two conductor, then I need to consider for the last one, that is three conductor open system. Will I get any of the common options here, like a series and parallel, because already it is existed. Series combination is done and parallel combination is also done. So we'll consider the same diagram. I'll just make it as this is also open. So I'll just rub this parameter. So now this is also acting as a open, is it? All the three conductors are open now. So we have A dash, B dash, C dash. So now what happens from the figure, you can say the sum of all the current is equals to 0. IA is 0, IB is 0, IC is 0. Overall, I can say that IA plus IB plus IC is equals to 0. I am not having any other option. If there is no current, then I cannot say nothing is going to happen in the system. So it says that your zero sequence is equals to positive sequence is equal to negative sequence is equals to 0. When you say overall system is existing 0, then what fault I can justify here? So you can say the analysis based on the system based on IA plus IB plus IC is equals to 0, or IA0 is equals to IA1 is equals to IA2. We say this is not a form of a fault at all, because it is acting as just an open circuit. I cannot say this is LG fault, LL fault, or LLG fault. I cannot say, I don't have an option to say that, because the complete current flowing through the network is 0, means no fault is existing. It is acting as a open circuit. Okay, so these are the three different types of faults in terms of series system, series fault under unsymmetrical condition. Clear? Any doubts on this?